It's not a map, it's a collage. You realize the world never looks like this, right? Like when it's light here, it's dark here. So I tell people that, and when some audiences, they're puzzled. They think this is the world at night. No, it's not. The world never looks like this. We're screwed. But you also see that there are big areas where there's no light. Now, there's only one or two reasons. Either nobody lives there or it hasn't been electrified. And so, from my perspective, if we want to give everybody on this planet the ability to participate, we have to electrify. I'm always amused at people that are working hard on MOOCs. They think MOOCs are going to replace in-person learning. And I'm of the polar opposite opinion. And you know, they like to tell the apocryphal story of the person in Africa who can have access to an MIT education. I'm saying, until you get electricity there, it doesn't matter. You know, electricity is everything. With electricity comes the ability to purify water, which comes health, which comes education, which is the antidote to poverty. So if you want to raise the standard of living in the world, you've got to start with electricity. And you don't have to connect here to the grid up here. You can put solar panels here, except solar panels are unreliable. They don't work at night. So how do you draw electricity from the sun when the sun doesn't shine? That's where the battery comes in. And that's why I work on it, because I see the connection. So storage is an enabler not just for renewables, but it's also an enabler for today's grid. You know, today's grid is designed for peak load. And the peak load is about 40% above average. And we only hit it about 2% of the time. So if we designed our highway system that way, I-93 would be 20 lanes wide in each direction. So that would mean anybody in this room could get on I-93 at any time and never tap the brakes. You say, that's crazy. I said, well, that's the way we build a grid. So instead, if we could go to average load, we might much better use of our capital assets. And the estimate is over the next 20 years, the world will spend about $17 trillion to modernize the grid. And if 40% of that is excess to meet peak, that's $7 trillion that could go in education, healthcare, and that. So this is a colossal waste. And then, you know, renewables are fine right now because they're a tiny fraction of our total grid supply. So, you know, the electricity powering the lights in here was generated just moments ago. And electricity is very different from any other commodity because the supply and demand have to be in balance. So the grid is the world's largest supply chain with no inventory. So imagine if every time you want to take a shower it has to be raining because we don't have the capacity to store water. And if more people want to take a shower than rain is providing, then we're out of balance. And if fewer people want to take a shower, then there's going to be spillage, and that's going to lead to disaster. Same thing happens with electricity. If demand and supply get out of balance by very, very tiny fraction, first thing that happens is the frequency migrates, and all of your electronic devices are betting. They don't care so much about voltage. Voltage can play a little bit, but they're betting that it's 60 hertz. And it's 60 hertz plus or minus 0.1%. And if that frequency migrates, all of a sudden you fry your devices. Can you imagine every time you went to plug in a device, you were wondering if it was going to get fried? And I don't mean to blow the fuse. I mean it's fried. You've lost it. So what happens when all of a sudden the wind picks up or the sun starts to shine, and we've got laws that say that the renewables get first priority, and the people that are transmitting electricity have to bring the renewables in. And then they've got to call the coal-fired plant or the nuclear plant and tell them, you need to ramp down by about 5% because we've just got this influx of new. It might take 15 minutes for that to take place. And during that 15 minutes, you know, the frequency's doing this. So we're lucky right now because we're down around 5%. We start getting up around 15, 20%. This is going to not be a problem. This is not going to be a solution. It's going to be a problem. And people don't talk about that. You know why? Because they want to be able to say it's not our problem. You see, because if you and I formed an oil company today, that company could be involved in exploration, drilling, pumping, shipping, refining, and selling to the consumer. But in electricity, the people who generate it don't transmit it. The people who transmit it don't sell to the ratepayer. So everybody's standing around looking and saying, it's not my problem, it's not my problem, it's not my problem. But when you plug that device in, all of a sudden it'll poof. Then they'll tell you, gee, you should have had a voltage stabilizer on your line. It's coming. So I made the case for storage. So why don't we have it if it's so compelling? Well, it's all about the money. This is capital cost, and this is installed capacity. This is a semi-log plot, so I know an MIT group can follow this. The only thing that works is pumped hydro, because everything else here, this is less than 0.1%, so it doesn't amount to anything. So all these batteries are useless. The only thing that works is pumped hydro. And pumped hydro is geographically limited because you need the difference in elevation. And the other thing that I take away from this graph is that if you don't get below $500 a kilowatt hour for the installed capacity, you're not going to make it. So there's two things. It's got to be cheap. It's got to be better than $500 a kilowatt hour. And it's not battery versus batteries. Don't ask me about somebody else's batteries because none of them are any good. You're competing against diesel gensets and natural gas. So if I'm going to take on, if an electrochemical technology is going to take on a thermochemical technology, man, you got to be really smart because it's not a fair fight at all. Because this is so much more energy dense and it's heavily subsidized and it's protected by the market and so on. You think if you invent a better mousetrap to just go and buy it? You know why the cell phone can be so quick to penetrate? Because it offers a functionality that nothing else offered. It didn't threaten anybody. But if I threaten petroleum, you think they're going to be greeting you with baskets of fruit and bouquets of flowers? No. And just to be clear, lithium-ion batteries fail bad. They're way too. It's 20-year-old technology. 20 years in. So you think that there are big, you think the gigafactory is going to find these huge cost reductions that haven't been found up until now? Really do? Good luck. Good luck. Gigafactory should be called gigafactory because it costs $gigadollars. $5 billion to build a factory? That's nuts. You know what I could build for $5 billion? I could build a greenfield integrated steelworks that would make 200,000 tons of steel a year. You're going to build a battery factory, build yesterday's batteries tomorrow. Good luck. So what's my approach? You confine chemistry to earth abundant elements. This is how I'm going to make something cheap. All right? And this is a plot I got from a government publication. And it's also a semi-log plot. And so this is the earth abundance as a function of atomic number. And yet somebody connected the dots. Now, what does it mean to connect lithium to beryllium? Is there an element with an atomic mass of 3.4? No. No. So, you know, when people say to you, connect the dots, you know, that's stupid. You know, sometimes you shouldn't connect the dots because there's nothing in between the dots. And the other thing that I learned here is that the difference between these elements and these elements is about 1 billion times. So it's a billion times spread. So if you're going to build something that's going to be big and cheap, you better build it out of something out of that part of the periodic table. And I refuse to allow my people to work in this part of the periodic table. They're forbidden because this is useless, it won't scale. So that's why fuel cells are a crock, because they're made with platinum. And do you think if the world demand for platinum goes up 100x, then the price of platinum is going to fall? No, it's a constrained resource. If the world demand for iron goes up by 100x, the price of steel will fall because it's an unconstrained resource. It's very different economics. You might ask yourself, why does GE work on cadmium telluride solar cells? Because tellurium is about as earth abundant as gold. So if I gave you tellurium for free, it still wouldn't scale. Figure out how many square meters of solar cell you'd need. And I don't care that it's got a higher conversion efficiency. If I told you it was 100% conversion efficient, so what? It doesn't exist. You realize that, no, I'll come to that later. So you want to make something dirt cheap, you better make it out of dirt. And preferably local dirt. Because it doesn't make sense to trade in your dependence on imported petroleum for dependence on imported neodymium. Your dollars are flying out of the country, it doesn't matter. So, you know, you look at windmills, what do windmills have in them? They got magnets. What are the magnets made of? Neodymium iron boron. Where's neodymium come from? Not here. The second thing is make it easy to manufacture. That's where lithium ion falls down. The gigafactory costs $5 billion. It looks like a semiconductor fab line. It should look like an automobile production plant. So when I started thinking about the liquid metal battery, I disregarded everything I know about batteries. Because I figured batteries are built to fit into devices like this. You don't take this and multiply it by 1,000 and get a battery that's going to serve the grid. That's stupid. So I said, let's look at the economy of something else. And my other area of research is electrometallurgy. So I looked at an aluminum smelter. I know it says aluminium because that's the UPAC name. And if you look at an aluminum smelter, it's bauxite, carbon, that's petroleum coke, 13 kilowatt hours of electricity to make a kilogram of metal. And the plant costs about $5,000 a ton. We can go from dirt to metal for about 50 cents a pound. That's why we have aluminum beer cans, because they're so cheap. And I said, that's a modern miracle. This is what modern smelter looks like. This is about, I don't know, 15 meters and goes back a couple of kilometers. It was invented in 1886 independently by two people, Charles Martin Hall here in the U.S. and Paul Heroult in France. There's Heroult, there's Hall. They were both born in the same year. They both died in the same year. And they met once, 1911, when Hall was getting the Perkins Medal by the American Chemical Society. And Heroult came from France to the banquet and spoke in praise of Charles Martin Hall. Even though they were fierce competitors, they had respect for each other. It's not like today in science, people are backstabbing each other. Well, if they were born in the same year, I guess they must have been the same age in 1886. Guess how old they were in 1886? 22. Two 22-year-olds changed the world. Because, you see, in 1876, that was the centennial of the United States. And a group of private citizens decided that there should be a monument in praise of George Washington, the first president. So they took up a collection to build a Washington monument. And they decided that the top of the Washington monument ought to be capped with a precious metal. It's a right square pyramid. And that square pyramid, weighs 100 ounces, and it's made of aluminum. Why? Because in 1876, aluminum was a precious metal costing more than silver. So there they are, putting the aluminum cap on the Washington Monument. It's still there to this day. But thanks to Hall and he ruled, they changed aluminum from a precious metal to a common structural material. But why? Because aluminum is the third most abundant element in the Earth's crust. And so if you change the process, you'll have an impact. If it's a rare element, it won't make any difference. By the way, silicon is the second most abundant element in the Earth's crust. That's why each of us has one of these, because the silicon micro devices are cheap. If our semiconductors were made out of rhodium, none of us would have one of these in our pocket. It would be so expensive. And by the way, what's coming after electronics when we sort of hit the limit on it? It's going to be photonics, right? Fiber optics? Well, fiber optics are made out of what? Silicon. Oxygen is the most abundant element in the Earth's crust, and silicon is the second most abundant element in the Earth's crust. So I know that in your lifetime, photonic devices are going to come because they're going to be abundant and cheap, because they're as cheap as dirt, because they're everywhere on the planet, dirt. We're lucky that photonic devices are not made out of tellurium and platinum, or else they're not going to come at all. So I just got to look at this in the periodic table and tell you what the future is. It's that simple. So we went from a common structural, from a precious metal to a common structural metal. They actually made two copies of this. This one on the top of the Washington Monument. That second one they put in Tiffany's on Fifth Avenue. And people lined up outside Tiffany's to walk through. And you were told that if you went in the line, they had this on the floor, and you would be able to step over this and then brag to your friends that you had leapt over the top of the Washington Monument. It's true. So now it's a common structural material. So in point of fact, a beer can sits on top of the Washington. So I looked at an aluminum cell and I said, well, why isn't it a battery? Maybe the aluminum industry is sitting right on the solution. And I realized the problem is that there's gas coming off the anode. And after some time, I figured out that you have to produce liquid metals in cold form. And so where the liquid metal is going to come from? So I go periodic table. And that was enunciated by a professor, Dmitry Mendeleev, who was the youngest of 12 children from Siberia, professor in Moscow. And he was 35 years of age when he enunciated the periodic table. How did he get there? Well, in 1869, we didn't have all of this. We had about 20 elements here. Some of the light ones, and then lead, and mercury, and gold. A lot of blank spaces. And he used to travel by train. And he'd sit on his trunk and he'd play cards. He played solitaire. They called it patience in the old world. Solitaire. And in his breast pocket he had file cards. And on the file cards he had information for each element that was known. You know, atomic mass, density, color, odor, some simple ideas. And so that's all true. Now this is my speculation, because I've read the paper from 1869. And so my speculation is that one day he's playing solitaire and he goes, okay, this is the ace of clubs, this is the king of clubs, some other suits, and now he's got the 10 of clubs, but he realized he can't play the 10 of clubs because it's ace and the king, but he's missing the queen and the jack, so he can't play the 10 of clubs. looks up here, and he realizes that he's got arsenic, and arsenic is next in atomic mass to zinc, but arsenic doesn't belong underneath aluminum. There's got to be a missing card there. There's got to be a missing card here. He called this ecosilicon. And then furthermore, he said, I want to predict what its atomic mass is. It's going to be 72. And sure enough, when they discovered germanium, it was 72. So it was not just the idea that we're going to organize them like this, but that I'm going to make predictions about what's missing. And that was truly brilliant. He was still alive until 1906, and the Nobel Prize Committee voted him down on 3 nominations for the Nobel Prize. You should look at what the Nobel Prizes were given for in chemistry from 1900 to 1905 and compare it to this. So, there's no, life is unfair. But anyways, this is really cool what he did. So I want to get maximum difference in electronegativity. So these are the best metals, the best electron donors, and these are the worst metals. I don't want non-metals, because if I got non-metal, I'll make gas. So I want to pair a bad metal with a good metal, get a good voltage, and so on and so forth. There's other physics. Magnesium on top, and antimony on the bottom, electrolyte, molten salt in between. This got a density less than 2, this got a density greater than 6, and density 3. No membranes, no separators, they just sit on top of one another. Oh, and I was able to do this with internal funds at MIT, thanks to the Deshpande Center and the Chassonis Family Foundation. If I'd written this up as a proposal, sent it to the Department of Energy, it would have been rejected as outlandish, or would have been stolen and taken to a national lab. But I was able to get started. So how does this work? Magnesium wants to alloy with antimony, so it can't dissolve in the salt, but if it becomes a magnesium ion, sends electrons through the external circuit, alloys with antimony. And then to charge it, you electro-refine magnesium back, so you purify the contents of the cell. And it's self-assembling, easy to manufacture. It's self-heating at commercial scale. The passive current generates enough heat to put insulation around it. The round-trip efficiency is 75%, which is greater than that of pump hydro, even after paying for the thermal losses. Some unithermal runaway, unlike the lithium-ion battery. And it's safe to ship. You can't ship lithium-ion batteries by plane. You have to go by boat, by truck, and by rail. You cannot put lithium-ion batteries on a pallet, put them on a plane. We've been to the Department of Transportation. They've said, well, what's the threat of this at room temperature? They said, well, it's solid metal and solid salt on a ship. The truck overturns on the highway, you get salt on the road. So we needed that anyways. It's been snowing. Now the question is it going to be cost competitive? This is my team, one person. David Bradwell. He looks pretty worried. He's wondering if this thing will ever work. And I met him. I told him, no, I don't think it'll work. And you want to get a PhD and you work really hard. And then it worked. And he was, sorry, I don't remember how to use all this phone. So his primary degree was in physics from Queen's University in Kingston, Ontario. So he was not steeped in the electrochemistry. I taught him as electrochemistry. So that's a theme that I've used a lot. That I bring fresh minds. That's what I like about being at MIT, bring fresh minds and bring them from outside. And that's served me well. And then a couple of years ago, the American Chemical Society did a profile on me, and they wanted a picture, so I sent them this image, and they refused to publish it. I said, what's the problem? I said, well, you're in the lab, and you're not wearing safety glasses. nonsense. I said, well, it's just a staged picture, it doesn't matter, this thing isn't real either. They said, no, we cannot show, we refuse to show scientists in unsafe dress in the laboratory. And I said, why don't you just take a Sharpie and just put it aside? And they refused. I had to find another picture. And, speaking of Aravis, electrochemistry began with Volta, a professor. He was a professor at the University of Padua in Italy, late 1700s. This is his first battery. It's a stack of coins of silver and zinc separated by cardboard soaked in brine. And with Volta's invention, he gave birth to a new field, which is electrochemistry, and also new technology. And very quickly it moved off campus for electroplating, electroforming, and it served the basis for electromobility. So Volta's invention actually gave birth to these new field and new technology, but also for the first time demonstrated the utility of a professor. And before Volta, nobody imagined a professor could be of any use, but Volta proved that being a professor alone, it's hard to come up with something that can be of societal value. And I think the whole notion of sponsored research derives from this, because this was research on a campus that gave birth to new technology. And then, so I just had that one student, we were looking along, and then the MIT Energy Initiative was formed. And I gave a talk in Paris and ended up with $4 million from Total. And then the ARPA-E started, and I was the first round winner in ARPA-E. And so now I had some real money. Now this is my team.